From the moon to the asteroids, the race for space resources could spark the greatest economic boom in human history. Why mine in space? When we think about mining, our instinct is to picture hard hats and tunnels, but the truth is that Earth is a planet that we've already dug deep. There's plenty more though. Earth outmasses our moon, every other moon, Mars, Mercury, and the entire asteroid belt combined. On Earth, the easy near-surface veins of gold, silver, and copper were tapped centuries ago, and every year we're chasing ores that are lower in concentration, harder to reach, and more destructive to the environment to extract. Mining remains one of the most polluting and energy-intensive industries on the planet, and the costs, both economic and ecological, will only keep climbing. Future technologies will likely help mitigate both concerns, as they already do to some degree, but space offers a very different equation. Out beyond Earth's crust, there are no delicate ecosystems to poison, no communities displaced by strip mines, and no mountains ground down for a few ounces of metal. Instead, we find an environment of abundance. Rocks and ice untouched for billions of years, many of them rich in the very elements that drive our technology and economies. Some asteroids are more metal than stone, vast chunks of nickel-iron alloy laced with platinum group metals. Others are loaded with volatiles, water, ammonia, and carbon compounds that can fuel rockets or feed space colonies. Colonies which may emerge around these future mining towns and establish a robust and prosperous foothold of new human settlements, helping us stretch out to the final frontier. And so beyond the raw material, space mining represents a technological pivot point. It forces us to develop autonomous robots, refining systems that work in microgravity, and space transport networks. Every step toward mining the heavens is also a step toward building a permanent, self-sustaining presence beyond Earth. Asteroids versus the moon. If you want to mine in space, you really only have two near-term targets, the moon or the asteroids. The moon is obvious, it's only a few days away. It has stable regolith to dig into, and it's already a target for international bases. It's rich in oxygen, though bound up in rocks, has useful metals like aluminum and titanium, and contains water ice in its polar craters. Its proximity means short supply lines and easy communication. Its relatively lower gravity makes it far easier and cheaper to dig out of the lunar surface and bring to space. The downside: lunar resources are generally lower grade, spread thin through regolith that must be baked, sifted, or chemically processed. The moon is a good quarry for bulk materials, but less so for concentrated veins of precious metals. Asteroids, on the other hand, are the lottery tickets of the solar system, some of them anyway. Many of them are ideal mines, small worlds where metals didn't sink into a molten core, but remained mixed throughout the rock. Indeed, many asteroids are the broken remnants of once larger bodies. A single kilometer-wide metallic asteroid might contain more nickel, iron, cobalt, and platinum group metals than humanity has ever dug out of Earth's crust. And unlike the moon, you don't have to fight against any gravity to haul it back up. The material is already in microgravity, ready to be nudged into a refinery or shipped home. Case study: gold in space. People talk a lot about bringing gold and platinum home from an asteroid and throw around terms like quadrillions of dollars. Now that's a bit exaggerated, at least in a practical extraction sense, but trillions is not, and even billions makes it viable. To get a sense of scale, let's take a small metallic asteroid, about 1 kilometer across. If it's a typical nickel-iron body, most of its mass could be nickel and iron, with tens to hundreds of parts per million of platinum group metals, PGMs, including gold. If we assume a mass of a 1 kilometer asteroid, with a density of about 5 grams per cubic meters, we get roughly 2.5 billion tons. There's a million asteroids that size in the belt, incidentally. We could reasonably estimate 100 parts per million gold, just 0.01%, and that works out to 250,000 tons of gold. For reference, all the gold ever mined on Earth in human history is only about 210,000 tons. So a single modest asteroid could contain more gold than all of civilization has ever poured out of Earth, alongside vast stocks of platinum and other PGMs. Now compare that to the moon's regolith, where gold and PGMs are measured in parts per billion, meaning it has way more gold since it has way more mass, but so diffuse it's hard to mine, much as the rest of Earth's crust would be. The takeaway is clear: the Moon is great for proximity and raw tonnage of common elements, but for precious metals, the asteroids win hands down. Let me add one caveat though: you have a lot of craters on the Moon. Those made by metallic ones are likely to have fairly intact or fragmented chunks, so the bottom of those craters, which also make for good bases, might have wads of metals in them too. Near-Earth asteroids, NEAs, versus main belt. When we think about mining asteroids, it's tempting to picture the main belt between Mars and Jupiter with its millions of rocky bodies. The long-term potential there is staggering, enough metal and volatiles to build more habitats than there are people alive today. But for the near future, those riches are effectively locked behind a wall of distance and energy. That's why the real focus is on near-Earth asteroids, NEAs, the small fraction of asteroids whose orbits bring them close to Earth. NEAs are easier to reach, easier to return material from, and much better suited for the first wave of mining ventures. Their proximity means cheaper missions, faster turnaround, and simpler communications. Some are just a few hundred meters across, but even the smallest of them can hold more industrial metals than humanity consumes in a year. The main belt, by contrast, is a project for civilization that already has a major space economy. Distances are measured in hundreds of millions of kilometers, travel times in years, and the delta V costs, the rocket fuel required, are several times higher than NEAs. The belt is a future prize, not today's opportunity. Case study: transport return costs for asteroids. To get a sense of why near-Earth asteroids are the early targets, consider the fuel costs. Bringing material back from a typical NEA requires a delta V around 5 km per second. Using a standard high-efficiency rocket propellant, such as liquid hydrogen and liquid oxygen, with a specific impulse of about 450 seconds, this works out to a mass ratio of roughly 2.9. In practical terms, that means you need about 1.9 tons of propellant for every ton of asteroid material you deliver home. In both cases, around 10 to 15% of that fuel mass is hydrogen, which you may have to import if you don't have native ice to use. The rest is oxygen and could be extracted from either that same ice, if present, or the rocket was refining the metal out of. Oxygen is a standard byproduct of most smelting operations, here or in space. Now, compare that to the main asteroid belt. Returning material from there takes closer to 15 km per second of delta V, and with the same rocket equation, the mass ratio balloons to nearly 20. For every ton of metal you want to deliver to Earth, you would need almost 19 tons of propellant. The result is hauling ore from the main belt costs roughly an order of magnitude more fuel than bringing it back from an NEA. That simple arithmetic is why the first wave of asteroid mining won't be chasing the riches of the belt, but will instead focus on the much nearer and more accessible targets right at our cosmic doorstep. Let's imagine we want to return a 10-ton re-entry capable pod with 20 tons of gold to Earth, 30 tons total. That would take 9 tons of hydrogen from your average near-Earth asteroid, and 124 tons for a typical belt asteroid. We are assuming they are locally sourcing the oxygen. We will also assume we need to deliver a package to each asteroid, all near-Earth and belt cases, of 100 tons of mining and smelting equipment, plus a 10-ton return pod and the hydrogen for that, which will be 119 tons total for the near-Earth case, and a whopping 234 tons for the belt case. To add to that, we also need more fuel to deliver each ton to the belt case. 1,046 tons of outbound fuel versus 251 tons in the near-Earth case. This would be made much worse by other fuels. Since hydrogen is hard to store by itself, you might be using another fuel or shipping something like methane, methanol, water, or ammonia out to use a stable high hydrogen source. Short form though, you are spending 4 times the fuel to reach the belt, and also requiring way more signal lag times and travel and return times. Now, estimating launch costs is always tricky, but while liquid oxygen is dirt cheap, liquid hydrogen can run several $1,000s a ton. However, that's still small compared to the few $1,000,000s a ton we currently pay to get to orbit. This is all napkin math, but the near-Earth mission launches for possibly hundreds of millions of dollars, while the belt case runs a few billion. Both are vastly cheaper if you're sourcing fuel off the Moon, but even without it, and ignoring the initial R&D costs, you are turning a net profit on return pod 1 or 2 for near-Earth asteroids, and maybe as early as pod 4 for the belt, though it has a lower profit per pod overall. Markets for space resources. When we talk about space mining, the most headline-grabbing idea is bringing home precious metals, gold, platinum, iridium, the sorts of things that send dollar signs dancing for the eyes of financiers. As we calculated, returning a 30-ton payload with 20 tons of gold from a near-Earth asteroid could net about 1.5 to 2.5 billion at today's prices. That is impressive, but it's also worth remembering that the Earth already mines several thousand tons of gold per year, and daily trading volumes of gold dwarf the output of one such mission. 20 tons will not crash the market, but the prospect of asteroid gold becoming routine might. Prices move as much on fear and expectation as they do on actual deliveries, and a working asteroid mine would signal to investors that future supply could arrive by the hundreds of tons. Another thing to keep in mind is there is a long, probably multi-year return time on a precious metal shipment from the belt, and not that much shorter for near-Earth asteroids, during which the pod could go off track, break, burn up in the atmosphere, or get hijacked, both in space and in the ocean when it parachutes down. That's where your actuaries come in and calculate how many tons of those metals you're actually getting as a ratio of what you actually mined. Those could result in high insurance premiums, or even folks selling gold or gold miner stock shares based on the photograph of the bars loaded into the pod before the return launch. At the time of this recording, the current spot price of gold is $124 million a ton. You might spend $40 million a ton on the overall cost of production and debt service on your startup loans, giving you an $84 million per ton profit, and make about 3 times what you spent. But then after accidents, theft, and the fact that you don't get paid for a couple years at best, that means you might prefer to sell that gold when the pod leaves for $62 million and wash your hands of it, pocketing that $62 million minus your $40 in cost for $22 million in profit per ton, and throw it into some 10% per year mutual fund or buy another pod to ship out there. Short form, it isn't very likely you'd crash the market. It's not free to produce nor instantaneous. You're not shipping 100,000 tons of gold home just because the entire rock has that much, meaning a mountain here on Earth probably does too. Digging it out takes time and effort, but at the same time, we would expect the price of gold, platinum, palladium, and so on to begin dropping to a bit over their production and shipping cost, and for both those to drop over time from space, and from new technologies for mining it here on Earth too. This assumes supply is keeping up with demand, obviously, otherwise even if you're mining it for $100 a ton, you might still be selling it for $100 million. But the assumption here is that the overall solar system supply is fairly bountiful, and there's no huge inherent roadblocks to setting up new mines. But the real near-term value of space mining may not be precious metals shipped home, but industrial materials used in orbit. For building space stations, power satellites, or even the first O'Neill cylinders, what you need are bulk metals: iron, nickel, aluminum, titanium, not to mention regolith and water ice. A single large habitat of the classic O'Neill design might require hundreds of millions of tons of structural material, and billions more in volatiles like water for life support, not to mention regolith to serve as shielding and soil. Moving all of that from Earth at current launch costs would be ruinous, but mining and processing it in situ from asteroids makes the construction of megastructures feasible. And again, it's not just metals. Volatiles like water, ammonia, and carbon dioxide are rocket propellants waiting to be cracked into oxygen and hydrogen, or the raw feedstock for agriculture and industry. We already have a growing market for these in orbit, and satellite servicing and refueling should become routine in the near future. More importantly, the infrastructure we've built for precious metal extraction has laid the groundwork for a broader space industry, lowering the cost of future mining and refining. In truth, that demand for propellants and volatiles is not some distant dream. It already exists today. And that demand will help us get asteroid mining started, and create a good feedback loop to other space industries. But even elements like phosphorus, essential for fertilizers and increasingly scarce on Earth, may be found in accessible asteroids, and could sustain both terrestrial farming and future colonies. Phosphorus goes for 1,000 times less money than gold, but we need it, and once you're established in space with in-situ fuel production, your cost for a shipment home might be basically the cost of creating the re-entry pod and digging out and electrolyzing a roughly equal mass of water to phosphorus. So what currently seems like an exotic luxury mission, a rocket tugging home a pot of space gold, may in truth be the lost leader that pays for the infrastructure to tap the real prize, a permanent, local supply of everything we need to live and build in space. As we've seen today, the first great space rush might not be for new worlds, but for new resources, metals, volatiles, and materials that can fuel civilization for centuries, almost like a giant scavenger hunt in space. And speaking of scavenger hunts, check out Scav, a brand new Nebula original from the Wendover team. It's a wild, hilarious, and surprisingly heartfelt look at the world's largest scavenger hunt, filmed over 4 chaotic days at the University of Chicago, and it's only on Nebula. While you're there, you can catch our monthly SFIA exclusive for November, Autonomous Space Industry, when AI and robots run the economy. We explore how robotic factories and self-replicating industry might one day build a civilization faster than we can populate it, and utilize all those resources we've been talking about mining today. Nebula is home to many thoughtful originals you won't find anywhere else. It's also where every episode of SFIA premieres, days before coming out on YouTube and elsewhere, and without any ads or sponsor reads like this one. Get a lifetime membership, normally $500 for just $300, by using my link go.nebula.tv/IsaacArthur, and unlock everything forever. Or get an annual plan for 40% off, $36 a year. That's 12 months for the price of 7. Scan the QR code or click the link below to start watching exclusive content like Autonomous Space Industry and Scav. Large-scale infrastructure needs. When we ask how big the market for metals in space might be, the answer is staggeringly big. Even a modest build-out of off-world industry implies demand on the scale of hundreds of millions of tons every year. If we value that metal at the shadow price of launch, what it would otherwise cost to fill up from Earth, the numbers run into the trillions. At today's best reusable rockets, it costs about $2 million to put a ton into orbit. Falcon Heavy, for instance, can bring it down to about $2.3 million per ton, while a rideshare slot on Falcon 9 might run $6 or $7 million per ton. So by that measure, the market value of 100 million tons of steel is in the hundreds of trillions of dollars. Even if launch costs collapse by 2 orders of magnitude, and we can deliver material to orbit for only $10,000 a ton, you're still talking about $1 trillion metal market in space. To ground that into something specific, let's start with the classical neocylinder. Suppose we want to build one new giant habitat every year. On the back of the envelope, you need about 100 million tons of steel for the structural framework, 5 billion tons of regolith to use as shielding and aggregate, another 5 billion tons of ices in the form of water, ammonia, methane, and other volatiles for your sea and sky. The regolith and the ice are bulk commodities, things you can sling around with tugs and mass drivers, but the steel is the core market metal. At $10,000 a ton, a price that assumes we have a mature in-space supply chain, that steel alone is worth $1 trillion a year. If you tried to lift it from Earth at the best near-term rates, such as Starship might do, $300,000 a ton, that jumps to $30 trillion a year. At today's $2 million per ton, it would be $200 trillion. And that's just the steel for one habitat, albeit one able to house 1 million people. That same sort of story plays out with other mega projects. Consider replacing all of Earth's power generation with an orbital solar power grid. The world currently uses about 20 terawatts of energy. Building a constellation of power satellites to beam that down by microwaves requires somewhere between 5 and 20 kilograms of hardware per kilowatt of generating capacity, depending on design. If you run the math, that's between 100 million and 400 million tons of equipment. Spread that over 20 years, and you're processing somewhere between 5 and 20 million tons of metal each year. At $10,000 a ton, that translates to $50 to $200 billion annually. At $300,000 a ton, it is $1.5 to $6 trillion, less than the annual energy sector. At $2 million a ton, it becomes $10 to $40 trillion a year in orbital construction costs. Ironically, given how big the energy sector is, even $1 million per ton lift to space might be economically viable. But how much better to get it far more cheaply off the moon, which is very abundant in silicon and aluminum. Then there is the solar shade, a giant parasol at the Earth-Sun L1 point designed to block just 2% of the sun's light, enough to help with climate control. The Earth's cross-section is about 1.3 times 10 to the 14th square meters, and 2% of that is 2.5 trillion square meters of shade. If we make that out of ultralight films with a density of 1 to 10 grams per square meter, That gives us between 2.5 and 25 million tons of film. Add another 20% for sparse metal frameworks and supports, and you are looking at another half to 5 million tons of structural material. If you spread that out over 20 years of construction and assume their service life is about that long, that is 25,000 to 250,000 tons of metal per year. At $2 million per ton, it's $50 billion to $500 billion each year. Now that would be well worth it for weather and climate control. That gets a lot more viable when you're spending 100th to maybe 1/10 that for production launched in space, not from Earth. Pull all these together, one O'Neill cylinder a year, an orbital power grid, and a solar shade, and the headline is clear. You're looking at metal market in orbit about 100 to 120 million tons per year. Priced at $10,000 a ton, that's over $1 trillion annually. At $300,000, 30+ trillion, and at $2 million per ton, well over $200 trillion a year. That's why nobody serious about building these things imagines paying Earth launch prices for steel beams and girders. It's only by mining asteroids on the moon, by smelting and forging in orbit, that these megastructures move from fantasy to feasible. But if you do, they become very feasible indeed. Technology and infrastructure for mining. Of course, to mine these places for resources you need mining equipment, and turning asteroids into mines requires tools unlike anything we use on Earth. In microgravity, you cannot rely on drills that push against the ground or dump trucks rolling over dirt roads. Instead, we need fleets of robotic miners that can clamp themselves to rock, cut or vaporize material, and sort it with centrifuges, magnets, and chemical processes adapted for zero-G. The general term is in-situ resource utilization, ISRU, and extends beyond mining to include turning ice into drinking water and fuel, extracting oxygen from rock, and refining metals into alloys ready for 3D printers or orbital foundries. Refining in orbit is as important as extracting. On Earth, ores are smelted in furnaces that rely on gravity to separate slag from metal, but in space you must rely on magnetic and electric separation or controlled rotation to mimic gravity for settling. We have already tested early concepts. The European Space Agency has cooked simulated lunar regolith with concentrated sunlight to extract metals, while NASA and private firms are experimenting with small robotic prospectors. These are prototypes, but the principles scale, and the future of metallurgy may look like swarms of automated bees chewing up an asteroid, feeding raw material into smelters and fab shops that never touch a plant's surface. Moving the material is its own challenge. Chemical rockets can nudge small payloads, but larger-scale transport will rely on tugs using solar electric propulsion, with ion engines or Hall thrusters pushing steadily for months. In the longer term, mass drivers, essentially electromagnetic railguns anchored to the moon or an asteroid, could launch cargo pods into transfer orbits without burning fuel. Some proposals even imagine wrapping an asteroid with a track and shooting processed ingots into space like machine gun bullets aimed at a waiting catcher's mitt in orbit, to mix metaphors. These sound wild, but each is a logical extension of technologies we already understand. Economic and political impacts. If space mining can move from prototypes to production, the result is not just new metals but new economies. We are talking about resource streams measured in trillions of dollars, enough to rival or surpass the oil and gas sectors that underpin 20th century geopolitics. The arrival of that wealth would disrupt markets in unpredictable ways. A single 20-ton shipment of asteroid gold is worth more than $1 billion, and while that amount is small compared to global production, the signal it sends, that more can follow, would shake commodity prices at least a little. Investors and governments would need to reckon with the risk of oversupply, just as oil producers dread gluts that drive prices into the ground. Precious metals could tumble in value if asteroid mining ramps up too fast, potentially bankrupting those asteroid mining companies who would be relying on a huge return on investment, a problem compounded by the psychological effect of knowing that there are entire worlds of platinum drifting above our heads. At the same time, the benefits of cheap bulk resources in orbit are transformative. Steel and water already cost thousands of dollars a ton just to reach low Earth orbit. If they could be sourced for pennies on the dollar from space, we could unlock habitats, solar power stations, and manufacturing networks that would otherwise be economically impossible. But the political consequences are as important as the economic ones. Nations and corporations that control off-world mining could find themselves in possession of wealth and leverage that dwarfs today's strategic reserves of oil or rare earths. Countries without space access could face resource dependency on orbital suppliers, flipping the script of terrestrial geopolitics. New spacefaring powers may emerge, while those left behind could struggle to keep pace. This is why the Outer Space Treaty and similar agreements, once seen as theoretical, may soon be the front lines of international negotiation. Who owns an asteroid? Who profits from its resources? And how do we prevent resource wars from moving into orbit? Long-term prospects. Looking further ahead, space mining is not just about making money, it's about building a civilization that can grow beyond Earth without choking on its own scarcity. Every ton of nickel iron mined from an asteroid is a ton that does not need to be lifted from a gravity well. Every tank of water drawn from icy rock is one less that must be ferried at an exorbitant cost from Earth's oceans. With those flows established, habitats can multiply, megastructures can rise, and industries can extend across the solar system. In time, the resource economy could expand to something unimaginable by today's standards. Instead of worrying about running out of copper or phosphorus, humanity could command enough material to construct entire orbital rings, kilometer-wide solar arrays, or planetary-scale shields. The main asteroid belt alone holds many thousands of times more metal than has ever been mined in human history, enough to build billions of O'Neill cylinders. If we can learn to use it, the bottleneck will not be supply, but imagination. From these foundations come the prospects of a solar system-wide economy, cities built inside spinning habitats, power grids that beam energy across planets, and space foundries that produce alloys stronger than anything we can smelt on Earth, and would all depend on asteroid mining. The shift would be as profound as the agricultural revolution or the industrial revolution, not merely an increase in wealth, but the creation of entirely new ways of living. This is why the space mining boom, if it comes, will not just be another chapter in the story of commerce. It may be the opening chapter in the story of a civilization that truly takes its place among the stars.